Couple of things, just business-wise. Today, we're going to start talking about conservation of linear momentum. And Thursday, then, we will talk about the moments of momentum, which is going back to some of those sprinkler examples that I used last Tuesday, when we ended up not having class together. My example there was really just about mass balance and sort of having these velocities going in different directions. We'll take that a step further with those types of examples on Thursday. But for today, we'll just talk about linear momentum in the context of flow through bends and things like that. Okay, so what I'm going to hopefully prove to you in the next couple of minutes or next several minutes is that we can use the conservation of momentum to back out a relationship to external forces. That is to say that the internal change in momentum or flow of momentum through a control volume is equal to the sum of the external forces acting on that system. Remember, the system is the mass of fluid that we care about here. So that's where we're going today and Thursday. Remember that from an email I sent you, I think last Thursday, just check your attendance or clicker grades online. Don't trust the one that's in the clicker or Reef app. Don't worry about those. I'm going through and figuring out if you were here on a given day and you responded to a question, I give you a 1. If you weren't here at all, and I can tell, because if you get a question or all the questions wrong, you'll have a 0. If you're not here, I'll see a dash, right? And so I can go through and sort of figure out the 1s and 0s. And it doesn't matter if you got them wrong. We're not grading you. You'll get a 1 if you were here and responded to the question, regardless of whether you got it right or not. So there's that. I set up individual participation grade book entries for every class that we've had. So that's lectures and recitations through the semester. Several of those, as I mentioned yesterday, are everybody gets a 1 because class was canceled due to snow or tragedy last week, things like that, or the midterm, everybody gets a 1 for that. Okay, so I filled those in as well so that they're accurate when we do the grade assessment at the end of the class, at the end of the semester. Midterm 2 is extra credit. I do have some extra credit that I want to offer you, so I'll give you details on the next slide. Midterm 2 is next Tuesday, so a week from today. Just a couple of notes about that. We'll go over this in more detail on Thursday, but we will have the same format. So there will be 10 multiple choice, true, false, fill in the blank type questions. There will be 5 to 6. It sort of depends on how the numbers fall out, but 5 to 6 short calculation questions. And then there will be the 2 long problems. So same format as last time. This time, I'm going to try to do a couple of things. One is I will try to make sure that the multiple choice questions are not super wordy. That is, dense text, and then reading a lot of text for each of the answers. So I'm trying to avoid those. Secondly, where we transition from multiple choice to the short calculation, I will type in short calculation in all caps and then a colon and then the question. Okay, and the reason I'm doing that is because I can't seem to find a way to format things, the quiz, so to speak, within Canvas, that quiz tool. I can't create separation between the different groups of questions. So I'll do that. And then the 2 long answer will say will be long calculation or something like that. And then the question. Okay, so hopefully that just helps give you a little bit of guidance. Let's see. So then for Friday at 5 p.m., we will have the solutions to the past. I think it's 4 homeworks. It's 6, 7, 8, and 9 will all come available to you. I will post some other sample questions for you to practice with. And next Monday during recitation, we'll go over some of the longer problems in preparation for the exam on the next day. Let me see what else. Homework 9 is posted. That's due day after tomorrow, before class. And then homework 10, I may not get posted by Thursday. I'll try, but it won't be due for 2 weeks. So my guess is that most of you are going to be thinking about the exam, which is the right thing to do. Put out the fire that's burning closest to you. In this case, the exam will come next Tuesday, and that's before the next homework will not be due the Thursday right after that. It'll be due the following week. So I'd be guessing if I picked a date at the moment, but it'll be basically 2 weeks from Thursday because we have the exam next week. Okay, so just as an FYI, that will get posted and it'll be due in 2 weeks. Okay, so let me go into the details real quick of this extra credit. What I have done, I'm summarizing the information here. Don't worry about writing down this link. What I've done is I created an announcement in Canvas, and it'll come live at 2:00 when we're done with class, and you can go click on it there. But basically, next Thursday and Friday, we have the 15th annual Hydrologic Sciences Symposium here at CU. It's all online. It's all virtual. So what I'm asking you to do is register. So you have to register to be able to attend because you'll get sent a link. But register and then attend for 1 hour during the 2 days. Doesn't matter what hour it is. Preferably not the hour that we're in class, that hour and 15 minutes. But pick an hour. Attend and watch whatever talks are being given. Now, you might be splitting between like a half-hour talk from an invited speaker and a couple of student presentations. I'm not exactly sure. It'll depend on what hour you choose. The program is not complete yet. It'll be finished by this weekend. It should be ready to go. But just as an FYI, you can choose your hour. And this is kind of basically like 8:30 to 5 on each of those days. Okay, so choose an hour, watch whatever is being presented, write down, take some notes about those presentations, and then all I want submitted by Monday, April 12th at 5 p.m. So the symposium is Thursday and Friday next week. The following Monday, just turn in 2 paragraphs. And those paragraphs are summarized as one, being an overview of the presentation or presentations that you saw, what was it about, and then secondly, a paragraph on how that presentation related to class. Now, not everyone is going to be talking about like velocity distributions and things like that. So even if it comes down to like mass balance or energy balance, that's fine. Okay. The idea is to just get you thinking about how fluid mechanics, even in the fundamental components, is applicable in a lot of different hydrologic or water related research. And then the Canvas announcement has this link to it and so forth. So click on the symposium, and then click on like register to attend or something like that. And you can, it's just a Google form you have to fill out. And mainly it will send you a link. I can't remember if it did it right away for me or if it'll do it next week, but you'll be in the hopper then to get the Zoom link when it's ready. Let me see. And you can get as many as 5 points. So imagine then that's like 5 extra points. That's kind of half of a homework assignment. That's like getting 5 extra points on one of the exams. It'll be 5 points. So consider that, and it could be if you do this poorly, we could give you less than 5 points if you actually turn something in. If you do it well, and it doesn't have to be stellar to get 5 points, it just needs to be solid, like a solid overview of what you saw, a solid overview of how it relates to class. And I'm not asking for 1 paragraph on everything you see or 2 paragraphs on everything you see. 1 paragraph summarizing what you saw in an hour, even if it's multiple presentations, and 1 paragraph about how those presentations relate to class. So just 2 paragraphs. Just make it a PDF when you turn it in. Okay. You won't yet see, I haven't created the place to turn that in, but it'll look like a homework assignment. It'll just be called extra credit or something like that. So you can just turn it in there. Any questions on that?
Oh, there's a question, I think you've somewhat answered, but it's like, what specific category will the extra credit go into? But I assume it's just all the points are added together. So
yeah, we'll probably just put it in your homework, but it'll, it's okay. If you got hundreds on all the homeworks, it'll be okay if you end up with 125 out of 120 points, something like that. So it'll just be added into the total. Yeah.
And then someone earlier had a question just for the exam. Will it include topics on the first exam? I guess, will it be cumulative, or will it only be on topics that we?
Oh, yeah, good question. I can't guarantee you won't see anything from earlier, but the focus will be chapters 3, Bernoulli equation, essentially, or energy conservation, and chapter 4, which was Reynolds transport theorem, and so forth. So mainly chapters 3 and 4 will be the focus, but I can't, you'll probably have to deal with something like, what did we deal with? Unit conversions or dimensions or something, right? I mean, those won't be the focus, but it's vertical learning here, so we will have a little bit of that built in, but the chapters 1 and 2 won't be the emphasis. Anything else, Alexi?
Someone just asked, will we have review questions like last time? And I think you might have addressed that last class.
Yep. So I'll post those by Friday. Those should be available to you.
And someone also asking if you're presenting during the symposium.
I'm not, actually. So I'm the co-director of the graduate program, and Holly Barnard and I, and we brought together this great group of graduate students to put together this symposium, and they have chosen other people, which is totally fine, but they get to choose who presents. So I will not be presenting, and you will not have to hear my boring voice for more than class on Thursday and Friday next week. So, all right. Emma just posted, I am actually presenting for 15 minutes, but. That's right, Alexi will be.
I don't know when, because I haven't set the times yet, but.
Right. The schedule will be coming out soon. So I'll let you know when I hear about the schedule. I'll send everybody an email just to let you know that it's available so you can help, if that helps you decide your time. If you're really constrained in your schedule, then you'll just have to pick an hour and you'll get what you get. So. Yeah. And if there are, by the way, there are a few hours, like from 2 to 3, where it'll only be 45 minutes of presentation and 15 minutes of a break. That's okay too. Just document for me what time slot, what hour you chose. And if there was a 15-minute break in that, that's fine. That's okay. All right. Okay. Terrific. Well, we've got a ways to go to talk about conservation of linear momentum, so we should probably get started. All right, let me get into pen mode here. So let's start with black today. All right, so our objectives today are to identify appropriate control volumes and draw corresponding figures. We've done a fair bit of that already, but in this case, we're going to think about what that means with respect to linear momentum. All right, we're going to use the Reynolds transport theorem to derive linear and moment of momentum equations. We're going to focus on linear today. Moment of momentum will be next this coming Thursday. And then we're going to calculate reaction forces using the momentum equation. What we mean by that is that we're going to derive a relationship or establish this relationship that tells us that the sum of all of the reaction forces external to a system can be calculated by looking at the sum of momentum fluxes and storage within a system. So we're going to calculate reaction forces. We're also going to calculate reaction torques. So remember, a torque or a moment of momentum is essentially a force times the length. So these reaction torques using the moment of momentum equation. So that we'll save for Thursday. All right, so let's start with Newton's second law of motion when we apply it to a fluid particle. So going back to fundamental basics here, we said that the sum of the forces is, of course, for a fluid particle is equal to the mass of that particle times its acceleration, right? That acceleration could be gravitational, or it could have to do with the velocity. So another way of writing that equation is to say that the sum of the forces acting on a particle are equal to the mass of that particle multiplied by the change in velocity with time. Now, we're going to assume that mass of that particle stays constant. In other words, that we are mostly dealing with incompressible fluids. So another way to think about this is that even though it's the velocity component of this relationship that might be changing with time, m times v, recall, is momentum. So we can look at how the change in momentum with time gives us the sum of the forces. Okay, so from a really fundamental perspective, we have just sort of exchanged acceleration with a change in velocity with time. But when we take the product of mass times velocity, we have momentum. So we're looking at a change in momentum with respect to time can give us a sum of forces. So that's fundamentally where we're starting from with Newton's second law. Sorry, I thought I was going to sneeze there for a second. As Alexi pointed out in a meeting we had earlier, this huge windstorm we had yesterday did a fine job of blowing pollen around, which is not great when we're all worried about whether we're sneezing because of COVID or whatever. So anyway, all right. So Newton 2, by the way, is just a shorthand for Newton's second law. So if we extend Newton's second law to a fluid system, the total momentum of the system can be written like this, which is to say that the integral over the system is v of velocity vector times rho dv. Now remember that I have two different v's here, and they mean two different things. The capital V with the vector arrow on top of it is a velocity vector. The V in the dv component at the end with the dash through it is the volume. Remember, so this is the integral over the system volume of V, the velocity, times rho, the density. All right. And then, so the second law, Newton's second law, then becomes some of the forces acting on the system is equal to d dt, so the change with respect to time of this integral of the system of v rho dv. Okay, so we've replaced acceleration with a velocity. change in time. And now we've just looked at how that's stored within a system. So we went from a particle to a system context, but again, we're essentially looking at the integral of rho dV is giving us all of the mass within a system, and we can look at how that mass has some velocity component to it to invoke momentum here. All right, so let's go back to the Reynolds transport theorem and consider the change in momentum of a system with using the Reynolds transport theorem. So that would look like this. That's weird. That's the capital D, dt of, recall that our fundamental writing of the Reynolds transport theorem had a capital B over the system, right? So some property is equal to partial of B in the control volume change with time. And I'm writing this kind of small because I have some two long terms to write out here. Plus, so here's our temporal. Remember, this is what we call the local derivative. And then the convective components are this sum of the mass outflow. So we have density of the outgoing fluid, velocity of the outgoing fluid times a cross-sectional area of fluid moving out or mass moving out, multiplied by, and then B here, right? Whatever our B is. So that's supposed to be an OUT. But U didn't come through very well. But anyway, that could be heat or whatever, or it could be momentum. All right, so that's what we're applying here. Minus the sum for all of the inflowing of the same property. So rho in, the sum of all of the mass fluxes in, so rho in, V in, A in, and then we multiply by little b in as well, right? So again, this could be little b, could be mass, it could be momentum, it could be acceleration, etc. Now, let's look for bookkeeping on momentum. We're going to set b cis, so this thing here, to the integral over the system with respect to its volume of v times rho, that product, and b in the control volume, so that's in the second term here, or the first term on the right-hand side, is the total momentum in coincident control volume. So it's the integral over the control volume of the product of the velocity vector times the density over volume of our system. And then little b is equal to the momentum per unit mass. So that ends up just being the velocity vector. Okay, so what does that turn into? So now what we end up with is d dt of the integral over the system. So all I'm doing is plugging in these three things into this general equation. I guess I could have written that out bigger. Didn't realize I had quite so much room, but in any event, the integral over the system volume of v, the velocity vector, times rho, dv now for volume, which is equal to, so that's the left-hand side. The right-hand side now becomes del t, where now we replace bcv with this interpretation here, the integral over the control volume of the stored momentum. So velocity vector times rho, dv now. So remember, we are integrating over the entire volume of the control volume, plus, and then our exchanges don't change. So we have this sum of the outputs of momentum. We replace little b with the velocity vector. So rho out, v out, a out, and then we have a velocity vector here, which is out as well. And then we subtract the sum of all of the inflows, rho in, v in, a in, and then velocity vector in. Okay, So one thing I want to point out real quick is the plus here and the minus here are already taking care of the velocity vector approach, or the vector approach where we looked at n hat. Remember, the normal vector, it's always normal to the control surface, pointing away from it. Therefore, the minus and the plus have already taken care of that. So the rho VA, so this component here and this component here, are already taking care of the general direction of what's coming in and what's going out. The reason that we don't have a vector then representation for this V, either of these two V's, the V out or the V in, are simply in those first parts, are simply because we've already taken care of the direction with the plus and minus here. The vector in the last V in each of these, though, is including a direction, okay? So little b is this momentum per unit mass, and it is a vector. So we have to be careful about which direction this flux is going with respect to our sign convention of X, Y, and Z. And then this one is also taking care of which direction the momentum is going. All right?
Professor?
Yeah.
Is the velocity out and the velocity in a part of that sum, or is that multiplied by the sum?
The velocity in this, can you see my cursor?
Yeah.
Okay. Do you mean this one right here?
The vector.
Oh, the vector. It is multiplied by this. So imagine this is like, another way of writing this is like the sum of all m dot ins times the velocity vector ins as well, right, for each input. Does that help?
So is that the sum of each m dot times v vector, or is it the sum of all the m's then multiplied by the v vector?
Oh, okay. I see what you're asking, Christian. No, it's the first one. It is the sum of each of the individual momentum fluxes coming in. So this is the mass component. We multiply out by the v in for each input. And then
so it's a part of the sum. Okay.
Yeah. Good question. Okay. So here's the equation, perhaps better typed than I wrote on the previous slide. But I want to now kind of make a point that we can break this down into English again, right? What is the sort of English interpretation of these four terms right here? They're kind of broken into three types. So on the left-hand side, this component on the left-hand side is essentially the rate of change of the system momentum. Okay, or the system's momentum. Remember, the system is our mass of fluid that we care about. All right, and we're going to distinguish that from this term, this first term, which is the rate of change of the momentum in the control volume. Now, we could say it's stored in the control volume, but that's a little bit inappropriate in the context of momentum includes velocity, right? So to say that you're sort of storing momentum would suggest that things weren't moving. So you could use storage if that helps, but just note that this is about what is at the moment within the control volume confines. And then, as we've talked about before with our Reynolds transport theorem, of course, this last section here, these two are quantifying the net flow or exchange of momentum. Oh, sorry. I'm just going to do net flow of momentum across the control surface, right? So there are going to be specific locations of inflows and outflows, and each one of these is the sum of each incoming sum of the outgoing momentums, each one of them that occur wherever there's an opening, and minus the sum of the inflowing momentums wherever they are occurring, the momentum flow in at each specific inflow to our control volume. All right. So, slight extension of what we've talked about before with respect to mass balance and energy, and now we're just applying it to momentum using the Reynolds transport theorem. All right. So this expression from the Reynolds transport theorem will be the right-hand side of our previous expression from the second law, Newton's second law. So remember, we wrote the sum of the forces acting on the system are equal to d dt of the integral over the system of v, the velocity vector, times rho, oops, it should be a rho, times integrated with respect to volume. So in other words, that is the shorthand way of saying that that's this guy right here, right? So now what we're going to essentially do is take all of this stuff on the right-hand side and set it equal to the sum of the forces acting on the system. So the left-hand side of our expression from Newton's second law will be the sum of the forces on the coincident control volume. So in other words, the sum of the forces acting on the system is equal to the sum of the forces acting on the control volume. All right. So if we basically say, okay, well, we're gonna make these two substitutions, then essentially all we're doing is rewriting this to say that the sum of the forces acting on the control volume are equal to the change in time of the integral over the control volume of v rho dv volume plus now those two long terms again, the sum of all of our momentum flows out, rho out, v out, a out, multiplied by the velocity vectors going out at that same location, each of those locations, and then we subtract the sum of the incoming momentum flows as well. So rho in, v in, a in, and then velocity multiplied by the velocity vector at each one of those inflows as well. Okay? All right. So that's curious. How did I end up with that? Oh, no, that's right. Okay. Okay, so again, I'm going to take this equation. I have it typed out on the top of the next slide. And what I want to note is that when we get to, there are several simplifying assumptions that we might come across. And one of them is if we have steady flow, right? For steady flow, remember that this term is going to go to zero for steady flow. So for steady flow, we would end up with a simplified version of this, which would say that I think I've been missing the vector notation on my force over the control volume. Sorry about that. But the force acting on the control volume, the sum of those forces is equal to just these two pieces right here. The sum of the exchanges or the net momentum flow through the control surface. So the sum of the momentum flow outs, the outflowing momentum flows, rho out, v out, a out, velocity out, the velocity vector at the same location, minus the sum of rho in, v in, not q, a in, times the velocity vector at the same inflow, okay? If it's also compressible, Then we take this one step further, and we could simply say that the sum of the forces acting on the control volume are equal to a really simple relationship here. The sum of all of the outputs of rho times q times velocity vector minus the sum on all inflows of rho times q times the velocity vectors associated with those. Okay, so steady flow, remember, gets rid of this temporal component at the beginning. When it's incompressible, we're just making v times a q. We would still get that anyway. You can see we still have the rows in here. Essentially, they would end up, we need them for the right units, but of course they would remain constant for both of these terms. All right, now we can also take this to all three directions. So the one thing about linear momentum that's important is that it has directionality to it. So we can have linear momentum acting in the x direction, acting in the y direction, acting in the z direction. So let's take this last equation we wrote and simply apply it to our three main coordinate directions. All right, so when we do that, we end up with, for practical applications, the vector equation is typically split into separate equations for each direction. So we would end up with the sum of the forces over the control volume acting in the x direction are equal to the sum of the outgoing linear momentum flows in the x direction. So the only thing that ends up with x is that, and then we write the second term. We have to subtract out all of the incoming momentum flows as well. So rho times q times vx as a velocity vector. And then we can write the same thing for the y, right? So some of the forces acting on the control volume in the y direction are equal to sum of all of the outflowing momentum fluxes. So rho times q times v y, velocity vector. That q looks terrible. Not sure why Wacom can't keep up with me here, but I'll try to write slower. Then we subtract again the inflows of rho q v in. Oh, sorry, not v in, vy. Sorry. So that should be a velocity vector for the in the y direction for each one of the y components of the inflow, and then again summing over the control volume of forces in the z direction is equal to the sum of the outflows of momentum rho times q times vz, where that is a velocity vector, minus the sum of the inflowing momentum flows rho times q times vz, where vz is a vector, velocity vector. All right. Okay, so that's it. Run with it. No, I'm just kidding. Let's put this to practice a little bit in a couple of example problems. The first problem we're going to sort of set up. We're not going to take it all the way through because we're missing a theta value. But one of the things that will help us do is sort of look at differences in some example forces. Okay. But ultimately, the way we use this relationship is to try to estimate the reaction forces needed to hold something in place. And that something will have fluid moving through it in some way. Right? So we're taking the momentum of fluid moving through a pipe, let's say, and using that to figure out what a reaction force is, what kind of reaction force is required to keep that pipe in place, for example. All right. So our first example is going to look like this. So this is a change in flow direction with, for lack of a better term, it's called a vane. It kind of looks like a ramp to me, so I'll keep it kind of simple. But we note a couple of things. One is that we have a V1 here, and that V1 is equal to, let me get this guy out of the way, V1 is equal to 10 feet per second. Yeah. And we note that it's coming out of a nozzle with an area of 0.06 square feet. And so we could calculate Q if we wanted to, right? Q would be 0.06 feet squared times 10 feet per second would be 0.6 cubic feet per second, right? So that's how much Q is coming out, how much flow of water. We see it's changing direction, it's sort of deflecting up. One of the things that I also want to point out is that here, so if we have our X and Z directions, right? We don't know anything about Y. Y is sort of going into or out of the screen here. Then we could say that we have all of our velocity here at 1 is in terms of an X component, right? So remember we used little u to talk about an X direction velocity component, and the W here, the Z component, is 0, as is the V component, or the Y direction, that is also 0. So it's all acting in the X direction. But then when we get up to here, of course, this velocity vector here, V2, will have both a U2 component and a Z2 component. Sorry, W. We were using little w for that. Little w2. Okay, so U1 is the same as V1 here. W1 is equal to 0. There's no vertical component to that flow that's coming out. Okay. The other thing that we could say is that for all of the flow Q that's passing at 1, that has to be the same as all the flow passing at point 2, which is to say then, okay, I guess these aren't very well labeled. I guess they're down here. For all the momentum coming in here, we have the same amount of momentum going out. It's just changed directions a little bit. The same amount of flow that comes in here is going out at point number 2, all right? So Q1 equals Q2, and we aren't really told anything about an area change. So while this might be a round nozzle with this flow coming out, and this may become more rectangular, we can assume that V1 is equal to V2, simply because, sorry, that was an error. V1 is equal to V2 because we expect that Q1 is equal to Q2, and we're not given any information about a change in cross-sectional area, all right? So we could also say A1 is equal to A2 as well. It may change shape from round to rectangular, but because we're not given any more information, we know that this has to be true. So we can assume that these two are true simply because we're not given any other information about how velocity might change in some way. Now, the components of velocity, V2 is the same as V1, but it now has a W component and a U component, right? A Z and an X direction, right? Okay, so now here are two reaction forces, and you'll notice that they are called FA. So FAX and FAZ are the two components. The A stands for anchor. So often what you see is what is either a reaction force or an anchoring force to keep this vane in place. So what this means then is that if this vane was light enough, let's just say it was 1 gram, I don't know what it'd be made of, but it would be very light. If we did not secure this vane in some way and we applied this fluid flow through it, or to the top of it and have it deflect and so forth, it would probably move if it was too light. All right. And sometimes what we find is that beyond the mass and gravitational force that holds this in place, we may need something additional. We may need to secure it in some way, right? And that's what this process is all about then, is figuring out this anchor force in the x direction and anchor force in the z direction. Now, both of these have been drawn as in the positive directions, right? Positive FAX, the x direction, is pointing in the x positive x direction, and FAZ is pointing in the positive z direction. We may or may not get positive values for those, but let's just work through this a little bit, and we can find out. Okay. So first of all, on this slide, let's see, I think I only gave myself one more slide to work on. So let's just work through the X part of this a little bit first. So the sum of the forces in the X direction are equal to, we're going to have this del T, for the sake of completeness, del T of the integral over our control volume of the momentum currently in the control volume. So note how the control volume has been drawn here. We have an input at point number 1, and output at point number 2. And we have our orthogonal V vectors shown here, V1 and V2. Okay, so the momentum that is in the control volume at the moment is equal to U times rho times integrated with respect to volume, plus then we're going to have the sum over the control surfaces of the momentum flow rate. So U times rho times the velocity vector dot n hat dA. And in this case, we're not given any information. We assume it's steady flow. So therefore, this term will go to 0, and we don't have to worry about it anymore. But we do have to worry about how this gets broken up to look at the exchanges. Okay, so one thing to take away from this then is that for steady flow conditions, in general, it's not the current momentum inside of our control volume that's causing an external force to have to keep this in place. Rather, it's the exchanges across the control surface. Okay, so the sum of the forces in the x direction are now equal to, and I haven't written out what forces that equals. I suppose we could write, let's see, where do I get to that? This is now equal to FAX, right? Yeah, we're just writing it in the positive direction. So let me replace this with just saying the force, the external force, anchor force in the x direction is equal to, and now we can start to break this up. So we'll have U2, so in other words, the x component of V2 times rho times A2, so that's the m dot flux, multiplied by the V2 magnitude minus U1, so this is now the inflow, times rho times A1 V1, okay? So if we could put numbers to all of this, we could be able to actually calculate what FAX is. Let me just pause for a second and create some translation between the U's, W's, and the V's that we have here. So U1 is, of course, equal to V1 coming in, and W1 we said was equal to 0. The little w, this is a lowercase w. So this is the z component of velocity. We can also note that the U2, because it's at an angle, remember V2 is at an angle, U2 is equal to basically V2 times the cosine of theta. But remember that we also said that V1 is equal to V2. So let's rewrite this and just put it all in terms of, that's supposed to be a V, of V1 times the cosine of theta. Now, I don't want to confuse you with that, but we're given V1 is equal to 10 feet per second. We know V1 has to equal V2, or we've reasoned that. So I'm just putting this back in terms of V1 because it's one number we can plug in. W2, on the other hand, so the Z component of velocity is equal to V2 times the sine of theta. And again, we can replace V1 with V2 because they're identical. And if we knew what theta was, we already know what V2 and V1 are, so we could plug those in. All right. Okay, so there's a start. On the next slide, what we're going to do is take this all the way through to a term in which we are calculating or coming up with FAX in terms of theta. So we're going to plug in now U2 here and U1 over there and work this out so that we get an answer, a number that's a function of theta, which isn't perfect, but again, this will allow us to at least look at the difference between these two, the FAX and the FAZ. All right, so now put in terms of V, and specifically V1 actually, we would end up with FAX is equal to V1 times the cosine of theta times rho A2 V1. So in other words, that's the outflow minus the inflow. Inflow in momentum is V1 times rho A1 times V1. So if we group these terms, then of course what we get is this is equal to minus rho A2 and A1 are equivalent as well. So we can simply say A1 times V1 squared times 1 minus cosine of theta, right? And we can now, remember we're working in, what are we working? Oh, feet, right? So we're working in imperial, so we can plug in a few numbers here. So this would be equal to minus 1.94 slugs per foot cubed. And then we multiply by cross-sectional area, which was 0.06 feet squared. And then we multiply by the velocity, 10 feet per second. And that quantity will be squared. And then we multiply by 1 minus cosine of theta. And, that's curious. Okay. And then we can take this one step further to just calculate all of this out. And FAX is equal to a minus 11.64 times 1 minus the cosine of theta. And that would come out to slugs times feet per second squared, which is basically mass times acceleration. So we would also just call this pounds if you wanted to, pounds of force. All right, so here's FAX, and note that it came out to be negative. What that means then is that the actual direction of FAX is acting to the left, not to the right. But we used our sign convention to put it in the right direction in our equation so that it fell out that way. All right. Now let's do the same thing with FAZ. So the sum of the forces in the Z direction are equal to, and now I'm going to I'm going to skip the step of crossing out the temporal change, but it's essentially equal to the sum over the control surface of little, goodness sakes, little w times rho v velocity vector dot n hat dA. So these are basically the net momentum flux across the control surfaces. So we can rewrite this as, let's plug in our W's. So we end up with W2 rho A2. So this is the outgoing momentum flow. And then we multiply by V2 here. And then we subtract the inflow W1, little W1, times rho times A1, A1, V1. And what we find from this, remember we said that W1 was equal to 0. So this guy is going to go to 0, right? So we're going to end up with, and now let's convert, now put it in terms. Oh, it is really struggling now. Come on, Wacom. In terms of V, we can now rewrite this as FA. Oh, and I'm going to say that this is equal to, I hadn't written this before, but FAZ, right? This is the force holding this vane up. So FAZ now, the Z component, the Z component, all right, that just looks terrible. The Z component of the anchoring force is equal to rho times V2 times A2 times, oh goodness sakes, times V2 times the sine of theta, which can be rewritten, remember, because V1 is equal to V2. So this can be rewritten as, goodness sakes, that's supposed to be a rho. Rho times, and A1 is equal to A2. So rho A1 times V1 squared times the sine of theta. And then we can plug into this some values that we have. So 1.94, goodness sakes, 1.94 slugs. Ugh. Per foot cubed. Really? And then times 0.06 feet squared. And then that's the area. So then we multiply by V1, which is also going to be a quantity squared. So 10 feet per second, really. That's supposed to be a feet, FT, that quantity squared, and then times the sine of theta. Okay, so this now equals, when we multiply this out, 11.64 times the sine of theta. And if we were given theta, we'd be able to figure this out basically in pounds, right? This would be a value in pounds. Good night. All right, that's a LB. Okay, so we don't have theta, but essentially here's our, oh man, FAZ. And on the previous slide, we had FAX. And if we just plugged in any theta, we could look at how these two change based on how theta changes, right? Okay, I hope that was somewhat useful. We're running a little low on time, but I think I can get through the next example. And right after that, we have the clicker question. So I might not get to the very last example that I have, but we'll start with that on Thursday. So example 2 here is now considering, we didn't consider the weight of the water in the previous one. We sort of made this a little bit simplified. Now we're going to consider the weight of the water and the weight of this nozzle. So imagine this gray nozzle on the left-hand side, and this little wiggly sort of dimension to it on each side is where the nozzle has threaded into this tip has threaded into the rest of, the pipe, the tube, whatever it's coming out of. So the nozzle has this kind of funky control volume that goes around all of this to be able to contain the water just in the nozzle tip. So it is this sort of looks like a vase here, right? It's got these this sort of contracting or component to it. So we're given a couple of things here. We're given a width. We've noted that W2 is a constant velocity on the downstream side. We have a uniform velocity here across the inflow as well, W1. This diameter is 16 millimeters at the opening, and it's 5 millimeters at the exit to the atmosphere. So first of all, let's start with, this is all going to be in the Z direction, right? We have nothing going on in the X or Y direction. So let's start with, one other thing for the solution. This is from your book. Rho is going to be equal to 999 kilograms per cubic meter. So rather than 1,000, if you had written rho is equal to 1,000, that's totally fine. State your assumption. To keep up with the way your book has done this is an example from the chapter. I'll keep 999 so that we get consistent numbers. All right, so on the right-hand side, I've left this blank because I want to fill it in with you guys to note a couple of things. So first of all, we know that we have some momentum coming out on the bottom, right? And that, I'm just going to call it little W2, oh goodness sakes, little W2 for the moment, and we will multiply it by the mass flow rate so that it becomes a momentum flow rate out. So that's a W2. We also have the W1 coming in up here, right, to our control volume. So there's W1 and W2. Those are the Z directions of velocity. We're going to have some anchoring force that we expect to be working in the vertically up direction. So FA acting upwards. I'm kind of drawing this maybe in strange places because I just want to demonstrate that they're all vertical, but if I draw them all at the same place, we won't be able to see them. We will also have the weight of the nozzle itself. And to identify these capital W's, I'm going to give them little wings like that. It's like Wonder Woman or something. But anyway, W sub N. And then we're also going to have the weight of the water, right? So whatever water is stored in the nozzle, we have W, oh goodness sakes, W sub W, right? Weight of the water in the nozzle. And then there are two additional forces here, and those are, I'm going to draw them to the side here a little bit. We have a P1, A1, so the pressure of water built up above, in this tube somewhere vertically is acting across this area. So there's a pressure force there. There's another pressure force right here, a P2, A2. Okay, so WN was the weight of the nozzle. W was the weight of the water that is technically in the control volume, but this is coincident with the nozzle, so I'm just going to say in the nozzle. And then P1A1 is a pressure force at 1, and P2A2 is a pressure force at 2, and little W1 is the inflow velocity, and little W2 is the outflow velocity. Okay. All right, which will represent momentums when we move forward here. Okay, so let's take a step at putting all of these together. We're going to say that the sum of the forces acting in the z direction here, so this anchoring force is what we're after, is equal to the momentum exchanges through our control volume. Again, the temporal component of the change of momentum within the control volume will be equal to 0. It's always constant, so it's not changing with time, assuming that we have a steady flow rate. And so we can write this momentum equation with the sum of the forces of z included. So sum of the forces in the z direction, I'm going to skip the part of writing the 0 that we're going to throw out, is just equal to the sum over the control surface of our momentum flow rates. Little w times rho times v, the velocity vector, times n hat dA. And we can now rewrite this as basically this integral being equal to, on the now I'm going to put all the forces together that we wrote on the previous slide. So this sum of the forces in the z, let's put all those forces now on the right hand side. So we're going to have FA acting upwards. We have minus the weight of the nozzle acting downwards, of course, because of gravity. And then we're going to have minus P1A1 simply because it's acting normal to the control surface, minus now this weight of the water in the nozzle, and plus P2A2. It's supposed to be a 2. Okay, so this component here can now be rewritten as a minus m dot 1. Okay, so mass flow rate, remember that's just rho times q. That's coming in on the upward side. It's got a direction that's going downward, so it is negative, times, oh, I'm sorry, I take that back. Let me think of the right way to do this. Sorry. Remember that the outs are positive and the ins are negative. So let's write this in that sequence. M dot 2 is the outflow of mass. When we multiply it by a negative W2, and the reason I write that it's negative is it is going in the downward direction, right? W2 is negative. Then that is there's no sign in front, or the plus sign more or less in front of the m.2 is because it is going out. Then we subtract the inflows, which is minus m.1 times, and now we also have a negative W1 because W1 is also going in the negative x direction. Okay, so the signs on the velocity components here are relative to their direction. The signs on the m dots are just relative to whether we are in the sum of the outflows minus some of the inflows, so whether you are inflowing or outflowing. All right, so that becomes that. On the right-hand side, we're still going to have FA in the positive direction minus the weight of our nozzle in the negative direction minus P1, A1 minus the weight of the water in the nozzle. And then this is going to be equal to 0 because the pressure as we go out through this jet is equal to 0. All right, so I'm just going to drop that at this point so that we don't have to consider it. So W1 and W2 are negative, or less than 0 because they flow downwards. Okay. All right. So now let's rearrange. Remember, we're trying to solve for FA here. So let's rearrange this and solve for FA. So FA is equal to, now some of these things on the left-hand side, we can kind of group and simplify. So we're going to have m dot 1, the mass flow at 1, times W1, little W1. And I feel like, oh no, that's right. Yep. So those two negatives give us a positive. Then we subtract m.2 times W2. So that is the momentum leaving at 2. And then we add our weight of the nozzle. So that's a force plus the pressure force at 1, P1A1, plus the weight of the water inside the nozzle, minus, and then I still had, I'll just scratch that out. I had the P2A2, but that should be 0. So, all right, so this should be weight of the nozzle, so that should be an N. All right, so what can we calculate? Well, we note that for all of the inflowing mass, we have to have the same inflowing mass as we have outflowing, right? It's not getting stored anywhere. So we can note that m.1 is equal to m.2, which we can just call m dot, right? Our mass flow rate. And so we could, I'm going to go ahead and calculate that, but essentially that would give us this guy and this guy calculated. We are given W1 and W2. We can calculate Wn because we're given the mass of the nozzle on the slide that we were given. We're also given P1, and we can calculate A1 from the diameter that was given. And then the weight of the water, we can do some geometry to figure out what this volume is and multiply it by the density. So m dot then is going to be equal to rho, and I'm just going to choose the inflow, rho times W1 times A1. We could have also said it's equal to rho times W2 A2. But this is equal to then 999 kilograms, oops, let me get one more 9 in there, kilograms per meter cubed is the density of water. And then we multiply that by 0.6 liters per second, which is our flow rate. Q, we need to convert that to cubic meters. So 1 meter cubed is equal to 1,000. 1,000 liters. And that comes out to 0.599 kilograms per second. And I guess that's all we need. So this should be seconds. Okay. So that will now go in to these two locations. W1 and W2 are given, but we need to convert them. For the sake of time, I'm not going to go through the steps to convert them. You could do that on your own, but essentially W2 is equal to W1 and W2 are equal to these flow rates. That flow rate, 5.99 kilograms per second. Q, 0.6 liters per second divided by a cross-sectional area after you do the conversions. W1 will come out to 2.98 meters per second. And W2 will come out to be 30.6 oh my goodness, meters per second. The Wacom is not keeping up. All right, and then I'll just also, note that N of the nozzle is equal to the mass of the nozzle times G, gravity. So that comes out to be equal to 0.1 kilograms. Oh, come on, that's a K. Kilograms times 9.81. Really? 9.81 meters per second squared, which comes out to be 0.981 newtons, right? So that'll get plugged in here. P1 we were given, A1 we can calculate, and the weight of the water then we can calculate as well. In the interest of time, I'm just going to write those out real quick. Just to note that W, and by the way, this is all written out in your book, so you can go check that out. But WW, the weight of the water comes out to be 2.84 times 10 to the minus 6. Oh, sorry, that was the volume. Sorry, this should be 2.78, pardon me, 0.0278 newtons. So that's a pretty small value. That weight of that water doesn't have a big impact. And we'll just multiply out for the P1, A1. So FA, FA is equal to 0.599 kilograms per second times 2.98 meters per second minus 30.6 meters per second. So what you can see is that the momentum balance is going to make that a negative, right, overall. And then we're going to add, that's supposed to be a bracket, 0.981 newtons. That was the weight of the nozzle, plus 400, now this is P1A1, 464 kilopascals, which of course we multiply by 1,000. 1,000 pascals per kilopascal. And then we multiply by the area, which is, oh, come on, pi over 4 times d squared, which is 16 millimeters. That quantity, that diameter squared, and then we have to multiply by, we just need to convert 1 meter squared is equal to 10 to the 6th millimeters squared, right? And then we'll close that bracket, and then we add the weight of the water inside of the nozzle is 0.0278 newtons. And when you work all of this out, FA comes out to be, well, let me write this out. Minus 16.5 is the momentum, plus 0.981 newtons, remember, is the weight of the nozzle, plus the pressure force is 93.3 newtons. And then we add the weight of the water inside of the nozzle, 0.0278 newtons. All right, so the weight of the water and the weight of the nozzle didn't have much to do here. The biggest were, in this case, these two values, which was the momentum exchange and the pressure force. So FA comes out to be 77.8. And because newtons, and because it's positive, that means that it is acting in the upward direction. Okay, sorry for going so long there. Let me just jump to the, I'll give you guys 10 seconds to kind of catch up writing all that. Again, this is an example in your book, your ebook that you can jump to and go through the rest of the details. So my apologies for keeping that succinct. The last thing I'll do here, let's just get to the, these are just some reminders that we'll go over. We'll start class with. All right, let's go ahead and get this started. So the question is, for the system from of basic laws, the momentum of a system can change as a result of A, pressure acting on the system, B, the gravity acting on the system, C, body forces acting on the system, D, surface forces acting on the system, or E, all of the above. So what are the forces that we care about that momentum of a system can change as a result of it? We'll just get up to minute here if everybody can get their responses in. Folks, we have 79. Oh, 79. Okay, perfect. Oh, 80. All right. We have a few folks working from the same computer. We'll just give it 10 more seconds here. 7, 6, 5, 4, 3, 2, 1. Okay. Oh, good. We got another. All right. So let's take a look. All right. A few of you sort of checked each one of these. 69 chose E, and it turns out that is the right answer. All of the above are possible influences on momentum change of the system. So good job, most of you. I think for anybody who thought it was just one of these, just note that all of these are things that can become those, some of the forces